All right, so my name is Karl Fuerlinger. I'm a postdoc on campus, and I work mostly on performance analysis tools. And this talk will sort of go back again to the more traditional ways in which to do parallel computing, mostly covering MPI and OpenMP and things like that. And so here's an outline. First of all, I'd like to give you a brief motivation of why people are interested in optimizing the performance of their code. Then the talk will have mostly two big parts. One is covering the basic concepts and definitions, mostly how do you do actual instrumentation, meaning how do you actually get insight into what the application does, how do you do the monitoring itself, and how do you analyze the data that you get back. And then the talk will cover three basic tools and cover their functionality. And these three tools are PAPI, which is a sort of a middleware layer which allows you to get access to hardware performance counters. OMPP, which is an OpenMP profiling tool, and IPM, which is used for to monitor message passing applications. All right, let's have a look at motivation. So while performance analysis in high-performance computing is important because these HPC centers are actually pretty large investments. If you consider procurement costs, which are in the range of about $40 million US, and then you have, in addition to that, you have operating costs of maybe about $5 million per year. And even power is about one megawatt per year costs you another $1 million. And often you have to build separate buildings for these computers. And so the point is just, these are pretty expensive facilities and equipment. And whenever you have a pretty expensive facility, then you want to make sure that you actually use it efficiently, of course. And so for the scientists which are using these systems, performance code is important because it allows them to solve larger problems. So it would allow them to actually have some new scientific discoveries with simulating more molecules or more atoms and things like that. And allows you to solve the problems faster and thus have a better turnaround time, test more hypotheses. Or it allows you to improve the error bounds on your simulations and thus to increase the confidence in your solutions. But also really on a smaller scale and down to handhelds, parallel performance is still important because in the end it's the parallelism that's supposed to enable new kinds of applications. But to be able to do that successfully, you have to really take the full advantage of the resources that you have, and you have to know where you lose performance maybe on the way. All right, so let's have a look at the typical performance optimization cycle. So you start out with your code development, and when the code development itself is finished, you hopefully have a functionally complete and correct program. And then you embark on this cycle of analyzing the performance and improving the performance. And you do that by measuring the code, by analyzing the data that you get out of it, and by modifying and tuning the code. And then you go back and test what the modifications, which kind of impact they had. And in the end, you hopefully still have a complete and functionally correct and a well-performing program, which you can then use in production. All right, so as it turns out, to actually be able to measure the performance, you often have to do something that's called instrumentation. And what will be covered in the rest of the talk mostly is in this box here. So the different techniques for instrumentation, the measurement, and the analysis steps. All right, so instrumentation is defined as the mechanism that allows you to get hooks into the application, figure out what the application actually does, observe the behavior of the application. And on the right-hand side here, you have a diagram. What typically happens when you think about your problem domain, write source code for it, down to when it actually executes potentially in a virtual machine. And there are lots of different levels and that add different abstractions to it. So you start out with your source code, then you might have a preprocessor that processes the code. Then you have a compiler, which compiles it into object code. You link in libraries like numerical libraries, BLAS libraries, FFT, and so on. The linker produces an executable, and the executable runs in an operating system, and the operating system itself may run in a virtual machine. And basically, on each of these levels, you can do instrumentation. You can add some hooks to figure out what's going on. And there are different techniques that come with different levels of overhead and accuracy on all of these levels. And of course, there's also a way to get away with not doing any instrumentation at all. And that's when you use a simulator, when you don't actually run on real hardware, but use a simulation tool instead. Well-known ones are called Valgrind or Symix. In this case, you don't have to change your actual application, and the simulation environment will give you all the information that you want to have. However, as it turns out, with these approaches, you typically have to deal with slowdown. So slowdown with typical simulators can be 50-fold, for example, and that kind of limits you which kind of applications you can actually use and run successfully in a simulator. Often you have to restrict yourself to very small kernels. And the other thing is, well, sometimes you really want to see how the real thing behaves on the real machine, and then you just have to do the measurement on the actual application. All right, let's look into some specific examples of where instrumentation can happen. One pretty widely used way in which you can actually get hooks into what's going on in the application is dynamic library interposition. That's instrumentation on the library level. So well, typically your executables are dynamically linked, meaning that at runtime, the application or the operating system will look up a dynamic library, and it will dynamically link in this library. And actually, as it turns out, what you can do is you can write something that sort of sits between the application and the operating system. So in this example down here, the application might issue a call getTimeOfDay, which just returns you the elapsed seconds since a point in the past, and which represents a date in time. And the operating system will give you back the date. Well, what you can do with a pretty simple technique, this LD preload technique, is you can write a dynamically linked object, and you can preload it in front of the application. So that way, any call to getTimeOfDay, if it's implemented in this library called timewarp.so, will actually be first handled by this library that you can provide. And the timewarp library can then, for example, actually call the time that just happened, and it can subtract, for example, in this case, 11 years to make you believe you are still in, this application still lives in the year 1999. And so this is a very simple example with just doing some timing, but this is actually used in practice for monitoring MPI, file I/O, CUDA, and CUDA programming. And that works because all of these mechanisms down here are implemented themselves as libraries, and you can sort of sit in between the operating system, the library that actually implements the functionality, and the application that uses it. All right, so here's another example for MPI, which is also library interposition. And as it turns out, the MPI standard itself comes with a mechanism that allows you to do an interposition approach. So the MPI library actually, if you look on the right-hand side here, the standard in the MPI standard actually prescribes that every function is available under two names. One is the standard name MPI send, for example. Then every function is also available under a second name called PMPI _ send. And the standard symbols, the MPI something symbols, are actually weak, which means that in the presence of another symbol of the same name, the other symbol will take precedence over the one that's implemented in the MPI library. And so what you can do here is you have this interposition library that sits between the user program and the MPI library, and it can itself provide the MPI send call, for example. And by doing that, you can write a tool that acts as a library and sits between the user program and the MPI library, and it allows you to intercept all the calls that the application makes. And to be able to finally actually send the message, there has to be a mechanism for the library to actually call the send routine in the library. And you do this by simply calling this PMPI version of the call. And the good thing about that is that it works for statically linked applications too. So for example, on Franklin, the system at NERSC, this operating system works with statically linked libraries. So this approach that I shown on the previous slide with the dynamic interposition would actually not work. But this static interposition using the PMPI interface of MPI works. And that's actually what pretty much all tools that work in the MPI space are using to measure the performance data. All right, another example for preprocessor-based instrumentation. So a preprocessor takes your original source code, pass it through the preprocessor, and then you get out a modified or instrumented source code. And here's an example of how this looks like for OpenMP. So you might have a very simple OpenMP parallel region where you just have this pragma OMP parallel, and then you have some user code inside. And with OpenMP, it turns out there are no standardized mechanisms to really get the performance data. So what you have to do is you have to do some kind of instrumentation on the source code level. And how this can look like and how this looks like in a specific tool called Opari is like this. So there's an instrumentation-based approach called Opari, which is a preprocessor that sits between your original OpenMP code, and it transforms it into this modified version where you have these hooks with the prefixes pump here. So in front of the parallel region, you have the pump parallel fork. Afterwards, you have the pump parallel join. And in the beginning, you have parallel begin and parallel end. And again, a tool can implement these hooks that are inserted by this Opari tool, and by that, observe what's going on in your OpenMP application. It can measure how long the total execution of the parallel region took. And with this stuff down here, it can actually also measure which kind of load imbalance you might have in your OpenMP program. All right. Then, of course, there is just plain and simple source code instrumentation. You can just add some hooks yourself into your code. And printf and get time of day are examples of that. However, it's actually, if you're already using a tool, it actually often is the case that these tools come with a mechanism as well that allows you to mark special regions of interest. So what you might want to do, for example, is mark the initialization, the main loop iterations and the data processing phases in your program, such that you can later analyze the performance data that you get out of the program with respect to these regions. And here's just an example of how this might look like. Opari, that's the tool that I just briefly showed before, allows you to do this pragma pump inst begin and pragma pump inst end. And in between there, you can sort of write your own application code. And the later tool will then know that you want to delineate these two, this application code block and call it foo, for example. And with MPI, it turns out there is a mechanism built into MPI as well to do that. MPI has this called MPI P control, and this is sort of intended for tool use, and it's not really described of what the implementation has to do with it. So the MPI implementation actually ignores these P control calls, but a tool that sits in between the application and the MPI library can do anything it wants with it. And in this tool, IPM, which I will talk about later, the way in which you can mark regions is by using P control 1 to enter a region and -1 to exit it. And again, you kind of have a way to delineate the regions that are of interest to you. All right, so this was the instrumentation step. The instrumentation step is a way to get hooks into the application to be able to observe what's actually going on. Now, we have this hook, and we have to measure the data. And it turns out there are two sort of broad approaches to measurement of data. One is called profiling, the other one is called tracing. All right, profiling is just a gathering of summary statistics, figuring out how many times a routine was called, for example. What's the inclusive and the exclusive time you spent in a routine? The hardware performance counters, hardware performance statistics, what's the call tree and the call graph and so on. And so typically how it might look like is like a pie chart that tells you how much time did you spend in an MPI send routine or things like that. And the second approach, tracing, is when you actually record each individual event that happened along a global timeline and record things like, oh, I sent the message, I was this process and I sent the message to this process and so on. So how this is typically visualized is a timeline. In this case, the time goes on the horizontal axis, and the vertical axis here are different processes. And this is from an MPI program. And whenever you see these black lines here, those represent message exchanges. And, well, tracing usually leads to quite a lot of large volume of performance data because you have this log of individual timestamped events, while profiling usually gets away with storing much less data. All right, a little bit more about profiling. All right, so profiling is very good to, at least as a first step, to exposing performance problems. And there is this 80-20 rule, or Pareto principle, which states that typically, or in many cases, you have 80% of your execution time spent in 20% of your application. And so the conclusion from that is that you should do profiling to figure out where you actually spend your time in your application, such that you can then optimize these regions where you do spend the time, and don't waste time on optimizing things that that don't have a lot of influence on the actual performance in the end. And turns out profiling can be implemented in two basic ways. One is called sampling, and the other one is called direct measurement. So with sampling, what you do is you use a mechanism that the operating system offers you, where you can periodically interrupt a running program and figure out where the program counter was. So the program counter is a register in the CPU, and it tells you which instruction the processor currently executes. And by interrupting the program and examining this program counter repeatedly, you can build a histogram of these program counter values. And if you do that very frequently, you get sort of a statistical distribution of where your program spends most of its time. Because the regions that are executed a lot show up a lot in these program counter values in the histogram. And that's actually used by a well-known profiling tool called gprof, and another one that's used in HPC a lot too. It's called HPC Toolkit. And measurement is just a direct insertion of measurement probes. So you just delineate a code block, insert the timer at the start, insert the timer at the end, and just take the differences between the times that you get out and use this to figure out the total time you spent in the region. So with respect to time that you get out of profiling, it's important to distinguish two different terms. It's inclusive and exclusive times. So inclusive time, let's look at this example here. So we have this function main, which takes a total of 100 seconds. And main calls this function f1 twice and the function f2. And let's assume that f1 takes 20 seconds up here and down here as well, and f2 takes 50 seconds. Then the inclusive time for main is 100 seconds, which just means it includes everything that main does on its behalf and all the child routines. And the exclusive time for main is defined to be just the time that main spends for its own computations, excluding any calls to subroutines. And the exclusive time is also called, in some tools, sometimes called self-time. And you can have similar definitions, not just for time. You can also have similar definitions for when you, for example, analyze hardware performance counters. All right, let's have a look at tracing. So tracing is this mechanism where you have a detailed timestamped log of events. And in this example, we have two processes, process A and process B. And A sends a message to B, and B receives this message from A. And what we are interested here is the enter and exit events into this routine master, and the actual send events that happen. And well, on the right-hand side here, you have the actual trace log, where you have to record the time when it happened according to a global timestamp, the location where it happened, the event that happened, and the context typically that describes which kind of additional attributes to the individual events. And well, once you have recorded this trace log, you can very easily draw pictures like the ones that I showed before as well. So you again have this context table that tells you what the context here means. Then you can transform this into a graph where you have on the horizontal axis the time axis, on the vertical the processes, and it shows you when the send and receive routines were entered and when the actual message exchange happened. All right, so this was instrumentation, measurement, and now analysis. So analysis is drawing some conclusions from the measured data. And it turns out there are two basic approaches to that. One is just a manual approach, where you use visualization to figure out what's going on, where you interactively explore what's going on, where you do statistics of it or drive a model. And then there are some newer techniques that try to automate the analysis process and try to cope with the huge amounts of data that you can get out of the measurement stage. All right, so for trace file visualization, there is a pretty well-known tool called Vampire, and it's a basic scalable version of the trace file visualization. So in this example, we have like about 30 processes here and the timeline here. And what Vampire allows you to do is it allows you to interactively zoom into the timeline here. So this is the shot number 2 here is zoomed in a little bit more, and shot number 3 here is zoomed in even more than that. And again, all the black lines here are message exchanges. And the green part is the application code, and the red part is the actual MPI application. It's the actual time spent in the MPI calls. So this is a very good approach to really go into the very details of figuring out what's going on in your code. However, as you can notice already at this scale of like 30 processes, it has some limitations with respect to scalability. So if you imagine that you run on a machine with 30,000 cores or something like that, visualizing that in a timeline display like that would not be very easy. And it would be very hard to actually derive some conclusions from that. So what you can also do with Vampire and also with other tools is have like communication topology graphs that show you how much data was exchanged between each pair of processes. So in these kinds of graphs, you have on one axis the sending process, and on the other axis the receiving process. And you could see how much data was exchanged between all these, between each pair of processes, essentially. Then what you can also do with another tool set, this one is called the PowerProf Year from the Tau tool set. Those implement an OpenGL viewer for performance data. So you load in the performance data in their format, then you can interactively explore graphs that you can look at. And so this works pretty well as well for an interactive exploration of the data. Now, with respect to automating the process of performance analysis, well, the main reason for that is really the size of the machines that we're currently dealing with. So typically now you have machines that are in the size of tens of thousands of processors. And Lawrence Livermore Lab actually plans to install this system called Sequoia, which is supposed to have 1.6 million cores. And a manual analysis with respect to tracing on the full size of that is just not likely going to work. And in addition to that, even at moderate sizes, if you do tracing over a longer period of time, you just get out gigabytes or even terabytes of trace data. And wading through all this data turns out to be very hard. So people have been looking into ways to automate the process of performance analysis. And so here's an example of how you can approach this. So in this example, we have 8 processes here. Process 0 sends a message to process 7. And as it turns out, the receive of process 7 started up here, but it could only complete down there when process 0 sent the message. Right? So this is called a late sender pattern because simply the sending side of the send-receive pair was late. And as it turns out, if you have the full trace, you can actually try to automatically detect this in the trace. And essentially, you have the waiting time from the start of this receive until the send was posted here as waiting time that you could have used differently on process 7. All right, so now I'm going to talk specifically about 3 tools, or 1 middleware and 2 tools. PEPI is this middleware layer that allows you to access hardware performance counters. OMPP is a profiling tool for OpenMP, and IPM is a profiling tool for message passing applications. All right, so hardware counters. As it turns out, hardware counters are actually embedded in all modern microprocessors. And they are specialized registers that have been put there originally and are still used for that to verify the hardware designs. So if chip designers design the chips, they have to have a way to figure out if it actually works correctly. And one way to do that is to have very, very specific counters that test specific functionality of the chip, like saying how many floating point operations were issued, how many loads happened, how many stores happened, and so on. And well, at some point, people figured out that you could also use these counters to do performance analysis, because floating point operations are interesting, and everything that has to do with the memory system is also interesting. And so people went out to see if you can use these counters and come up with a standardized interface to access them. And so, as it so happens, PAPI is now the default interface to use those counters. And it allows you to get pretty detailed insight into the caching behavior of the processor, branching, pipelining, pipeline stalls, the floating point efficiency, and it allows you to do basic calculations such as how many instructions did you execute and how many cycles did it consume. So with respect to counters, it's important to differentiate between these two things. One is counters, and the other one is events. And usually you have a very large number of countable events. These can be in the several hundreds, while you only have a small set of actual physical counters on the chips that allow you to count certain things. So you have to program the counters to count a certain event. And there are also restrictions on what can be counted simultaneously with other settings. And PAPI actually handles these restrictions for you, and it also allows you to do multiplexing if needed. So you can actually count more things simultaneously than the hardware would allow you by dynamically switching out the counter sets. So, as I mentioned, PAPI is sort of a middleware layer that you can use directly in your application, but it's also most often incorporated into tools, and you most often use it actually through tools. And the countable events are defined in two ways. There are platform-neutral preset events, and then there are these native events. The preset events come with a prefix PAPI. So, for example, PAPI total instructions counts the total number of instructions that were executed. And the native events are just whatever is supported by the particular platform or CPU. And the preset events here are just derived from a linear combination of the native events. And these presets, they were an effort by the PAPI team to sort of have a standardized set of counters across different architectures. But that only is done in a sort of a best effort manner, because the counters and the events are very different. They have very different semantics on different architectures. So sometimes you can't really guarantee a semantic equivalence between different architectures for the preset events. So PAPI tries to do the best to preserve that equivalence, but it can't always guarantee it. And actually, it turns out this hardware counter business is a pretty messy stuff. So if you really want to figure out what an actual counter counts and if it does so correctly in all circumstances, that can be very, very tricky sometimes. So as I mentioned, the presets, that's a set of over 100 events that have been standardized by the PAPI team to try to have this standardized set over different architectures. And there is a tool that ships with PAPI called PAPI Avail. If you execute that, it will give you a list of all the available presets. The natives, on the other hand, are just anything that's countable by the CPU will be exposed by PAPI. And there's this other tool called PAPI Native Avail that allows you to see all the native events that you can count. And PAPI also ships with a tool called PAPI Event Chooser, which allows you to figure out the set of counters that you can count simultaneously. Because, as I mentioned earlier, there are certain restrictions. You cannot count any event at the same time as with any other. So the PAPI Event Chooser allows you to build a set that you can count at the same time. So PAPI sets up on the perf counter hardware, then it needs operating system support to access the counters. And until very recently, you had to actually patch the Linux kernel, for example, to have access to the counters. With more recent Linux kernels, there is a built-in interface that allows you to get access to the counters. But previously, you had to apply a patch to get the data. And then PAPI has sort of two layers to it. And as I mentioned earlier, it's most often actually used through tools. PEPI comes with a low-level API, which gives you full control over what you want to do. And it comes with a high-level API, which is a very simple way to get very basic measurements, such as the floating point operations and so on. So here's actually all calls in the high-level API. It just allows you to get the number of counters that you can count simultaneously, and it allows you to just have one call to set up, to figure out how many floating point operations did I have in a specific code block. And I won't go into detail of that, but that's how a low-level library usage looks like for PEPI. And this all is centered around the concept of event sets, which are the events that you put into a set and want to count at the same time. And then you can do things like start the counter, stop the counters, read them, and so on. And yeah, most often you actually use PEPI through tools. So most of the tools will incorporate PEPI and will allow you to select counters that you want to count by, for example, setting environment variables. For example, for the IPM tool, which I will talk about later, what you set is I set this environment variable IPM HPM to a list of counters that you want to count. So in this case, we want to count the floating point operations, for example. All right. The second tool I'd like to talk about is called OMPP. It's a profiling tool for OpenMP codes. And I believe OpenMP was covered on Monday, right? So how OMPP works is it has to rely on source code instrumentation because, as I mentioned earlier, there is a well-defined interface for MPI, but there is no well-defined performance tools interface for OpenMP. So all you can basically do in a platform-independent way is transform your source code using a preprocessor approach to insert these hooks. And so you start out with your source code. You do the automatic instrumentation of the OpenMP construct, and in addition to that, manually mark regions of interest. Then you produce an executable link in the library, and you execute it on your parallel machine. And depending on some environment variables, like the selection of hardware counters and settings, you get out a profiling report. So OMPP is based on the source code instrumentation approach, and is thus pretty portable and widely usable on many architectures. The profiling report gives you basic information such as the date and time duration of the run, an overview of which kind of regions you had in your program. It gives you a flat region profile. It just tells you how much time you spend in certain parts of your program. It shows you the call graph or region nesting of your program. So it tells you, for example, the nesting between parallel region and critical sections and so on. And it gives you call graph profiles, which include the inclusive and exclusive times. And it tries to do an overhead analysis report. So what that about is when you execute your program in parallel, you usually encounter some kinds of overheads, such as imbalance, load imbalance, for example. So, for example, if you divide a loop onto 4 processors, the execution might not be load balanced. And if you have an imbalanced execution, that shows up as an imbalance overhead in this overhead analysis report. So here's a very simple example of how the output looks like in OMPP. So this is a very simple code fragment. It's just this parallel region. And the parallel region contains a critical section. And the critical section just contains this sleep call for 1 second. So this makes the thread that encounters this critical section sleep for 1 second. And on the right-hand side here is how this critical section profile looks like for an execution with 4 threads. So the first column here gives you the thread ID. So we see that it was executed with 4 threads, TID 0 to 3. And the last line here sums over all threads. And then you have a number of columns here, which represents either times or counts. So in this case, we see that XXC is always 1. So each thread executed this critical section once. XXT is the total execution time of this critical section. Body T is the time inside the body of the critical section. So this just goes from here to here, which just covers the sleep for 1 second. Enter T is sort of the most interesting aspect about the critical section here. It's the waiting time that's required to enter the critical section. So the semantics of critical sections in OpenMP are that all threads that encounter the critical section can only enter it one after the other. So if we start this program with 4 threads, inside of the parallel region, we will have 4 threads, and then only one at a time can enter the critical section. And this profile actually tells us the sequence in which these threads enter the critical section. So in this case, thread number 1 had 0 seconds waiting time. Thread number 2 had 1 second waiting time, and then thread 0 entered, and the last one was thread number 3. And so this sort of gives you basic information of what happened in your program and how much time you spent in the total construct and how much time you spent waiting, for example, to enter critical sections. All right, so here's a complete table of the timing data that's reported by OMPP. So on the left-hand side, you have all the OpenMP construct, and there is a dot essentially whenever there is this time is reported by OMPP. Now to this topic of overhead analysis. So if you go back to the previous example of the critical section here, this enter time here is just idle waiting time. So this thread 0 here waited 2 seconds to enter the critical section. It didn't do anything else on your behalf. So this represents an overhead. And similarly, some of the other times that are reported here represent overheads and waiting time that's not used on your behalf in your program. And based on this observation, you can sort of define 4 different overhead classes. One is imbalance. That's just the waiting time that's induced by an imbalanced amount of work. Synchronization overheads, that's when threads have to synchronize their activity with one another. Limited parallelism, that happens when you actually have more available threads than work items to do. And thread management, that's the overhead that you incur when you repeatedly start and stop parallel regions. And so this is the same slide as before, and it's now colored with the different overhead classes. And it turns out actually a lot of times that you can measure actually correspond to overheads. So for example, the critical section from earlier, the enter time, the time required to enter the critical section is considered a synchronization overhead. And that's an example of a program and how the overhead analysis report looks like. So it gives you sort of a very high-level view of what your program did. It tells you that the total runtime in wall clock of this program was 170 seconds, running with 32 threads. It tells you that you had a total of 12 parallel regions, and that the parallel coverage, meaning the time that you actually spent covered in parallel regions, was 78%. So this allows you to tell if you can actually expect some speed up from running with more threads. And then down here you have the actual overhead analysis. So R11 here identifies a particular parallel region, and in this case we would see that about 18% of the execution time in this parallel region was spent in certain overheads. And in this case we see that most overheads actually had to do with imbalances, with load imbalances. And down here you have the same numbers, the same absolute numbers, but the percentages are computed with respect to the total execution time. And it's also sorted by the most contributing regions. So in this region, if you go to the top left part, it would tell you the parallel regions that have the most overheads, and thus would likely be optimization targets. Now, what you can also do when you identify these overheads is you can analyze the scalability of programs. So we have classified the total runtime into work and these 4 overhead classes. Now, what we can do is we can run the same program with an increasing number of threads. So we would run our program, for example, with 1 thread, and we would record the wall clock time. Then, if we run it with 2 threads, we would expect that the wall clock execution time halves, ideally, right? But if we look at this on the right-hand side, we just accumulate the time that we record and stack it on top of each other. And similarly, we run it with 3 threads. Ideally, it all adds up again to the same amount if we sum all the threads. And the same with 4. So in this kind of display here on the right, we see that a perfect scaling is represented by a horizontal line, right? If we sum all the threads, perfect scaling would be represented by a horizontal line. And if we go above the horizontal line, we would have imperfect scaling. We would have some overheads that contribute to a slowdown as we increase the number of threads. And if we can actually go below the horizontal line, we would have a case of superlinear scaling. So here's an example of how this actually looks like in two small benchmark applications. So these are from the NAS parallel benchmarks. EP stands for embarrassingly parallel. It's known to be an application that scales very well. And as we increase the number of threads from 1 to 32 in this example, we see that the runtime almost stays exactly the same. At the very end, so I should say, the roof here is the total wall clock runtime, and then there is a breakdown into the overheads that we can measure. So the light green part here is imbalance overhead, for example. But whatever is left over when we take the total wall clock time, subtract all the overheads, we call this work. So in this example on the left here, we see that this application scales very well. Only at the very end, there is a little bit of an imbalance. SP on the right-hand side here scales far worse. And we see that as we increase the number of threads, what gets to dominate the overheads here is load imbalance. Here's another example of where you can actually see superlinear speedup. That's an application from the spec parallel benchmark suite. And at least as you go from 2 to 4 processors here, you see that the accumulated wall clock time actually decreases. And well, what can be the reason for a superlinear speedup? Well, the most likely reason for a superlinear speedup is that you start to benefit from an increased overall cache size. So if you go from 4 processors here to 8, turns out in this particular machine, you also increase your cache that's available to your program. And so the data set that's worked on by this application just fits into the combined cache better. And thus you can actually get a superlinear speedup. And in this case, we actually measured the data. And so this is the level 3 cache misses. And as you can see here, if you go from 4 to 8 threads, you actually see a pretty significant drop in the number of L3 misses, which most likely contributed a lot to the superlinear speedup here. Here's another example. This time it's actually scaled out to 128 threads. And in this case, actually, it turns out the management overhead, thread management overhead, is pretty significant. And in this particular code, it turned out that there is just a very small reduction operation that reduced the scalar operation. And at that time, this reduction operation was not optimized for this machine. And so it turned out that this operation actually dominated or started to become a pretty significant factor for this code. All right, the last tool I'd like to talk about is a profiling tool for MPI applications called IPM. All right, IPM stands for Integrated Performance Monitoring. It is, its purpose is to be a pretty thin measurement layer sitting between the application and the runtime operating system. It started out only as an MPI tool, but has recently also been extended to cover other things, such as OpenMP as well, File I/O, and we're working on a CUDA implementation of it too. With IPM, the goal is really to be as efficient as possible with respect to monitoring. And IPM is really only interested in pretty high-level performance metrics. We'd like to get an inventory of the events that happen in the program, and we'd like to determine which kind of resources the application used on a high level, how much memory it used, what was the total floating point rate, and things like that. And it has less focus on an actual drill down into the application. So there is no automatic mechanism implemented to instrument individual functions, although you can also do the manual region instrumentation. So with IPM, what we'd like to do is that you just sort of flip a switch to enable the monitoring. So if you usually have this, you take your input, you have a parallel job, and you get the output, and this flip of the switch would allow you to link IPM to your parallel job, and in addition to your usual output, get out the job profile that tells you the most basic aspects of the program execution. And in IPM, this output comes in basically 3 forms. One is just a banner that gives you very basic information that's written on standard error immediately after program termination. And then there is a more detailed profiling log that's written in XML format. And then you can take this profiling log and transform it into a profiling report that's written as a web page in HTML format. All right, and to do this, we try to be very efficient with collecting the event statistics, and we use a hash table to do that. And we use operating system interfaces like /proc to get at the resource requirements. So for MPI monitoring, what we essentially do is we capture all the MPI calls. And whenever we have the MPI init call, we initialize the monitoring environment, allocate memory, and so on. And finalize, we aggregate all the data from the different tasks. We write it into one log file. And for each other call, MPI call that's done in between, we store the most important aspects of it. And we do this by using a hash table. So we compute the hash key from the type of call and buffer sizes and things like that. And then we store and update the value that's associated with this key. So here's how this hash table or this hash key basically looks like. It captures things like which type of event was, which type of call was it, in which region did it happen, which thread did it happen in, what was the buffer size, what was the communication partner, for example. Then we take this key here and transform it and use it to index into a hash table. And in the hash table, we store things like how many times did this event happen, what was the minimum duration, the maximum duration, and the average duration. So this is a pretty simple concept, but it turns out that if you analyze the data in the hash table, you can get out a lot of things. So this is a very simple example. It's just a pie chart that tells you how much time of your MPI time was spent in different types of MPI calls. So how much time was spent in the getter operation, scatter operation, all-to-all, and so on. And that's included in the hash table, of course, because one of the fields that we index in is the type of MPI call that we used. Then we also have this communication topology graph, because what we also store is what was the partner of the call. So if we do a send and receive, we have a different hash key. If we do the send and receive, we store the partner, the sending and the receiving type, and different partners lead to different hash keys. So we can analyze the data in the hash table also to create this communication topology, where each pair shows you how much data you spent between pairs of processes. And we can even do an analysis of the data with respect to buffer sizes that you used. So on the horizontal axis here, you have a log display of the size of the buffers that you specified for your MPI's messages. So, for example, this tells you that, so all these lines are for different operations. The red line, for example, is for a getter V, I guess. And all those graphs go from 0% to 100%. So it accumulates where you spent the time, depending on the size of the buff on the operation that you used. So by looking at this kind of graph, you basically can tell you where you spent most of your time. So you would look for the area where you have the most increase, where you have the biggest increase. And you could use this information, for example, to optimize your code with respect to trying to get bigger messages and collecting, aggregating messages together. Right, so as I mentioned, with IPM, we really like to make it as simple as possible to use. And well, the simplest way you can currently use IPM is you do a module load IPM, and then you just run normally. And what happens behind the scenes is that this LD preload mechanism is used, and it interposes the IPM library with your between your application and the MPI library, and it does all the monitoring for you. So this only works on machines where you have these dynamically linked libraries. And on Franklin, for example, which is a statically linked architecture, you actually have to include IPM on the link line with your application. But IPM is available on the Franklin machine, and it should work there. And then when your job completes, you just get this banner out. And the banner gives you the most important information. It tells you what your executable was when it ran, what the host was, what the total runtime was, what was the communication percentage. It has information on OpenMP if you used OpenMP in your program. It tells you how many files you used and things like that. And also tells you what the total memory usage was of your program. Then you can set an environment variable called IPM Report. And if you set that to full, you get sort of a more detailed profiling log. And this more detailed profiling log gives you, in addition to that, to the top part, it gives you information such as what the distribution was of these metrics across different ranks. So the min and the max here would be across different MPI ranks. And down here, you would have even more details about the contribution of individual events. So this would tell you that you had about 22% of your time was spent in MPI all reduced, for example. And in addition to that, I mentioned that IPM writes a log file in XML format, and you can take a parser called IPM parse and generate a web page from that. And it turns out this format is actually pretty well capable for permanent storage of your profiling reports. So it's independent of the particular operating system. You just generate this web page and the graphs, and you can later go back to that and look at the performance. All right, so IPM is really good to have an initial reading on the performance that you get out of your application. It allows you to get basic information such as what's your floating point rate, what's your communication percentage, what's the ratio of computation to communication, and things like that. And it's also, even though it has limitations with respect to the drill down into the particular application, it's also sometimes actually surprisingly successful. So this is an example from an actual code that I think was in production use as well. And the question here is, what's wrong with this code? And well, if you look at this pie chart of the communication percentage, we see that there is a lot of time in MPI all reduce. Right, so this might be a problem, but that very much depends on the particular application. We also see that the second most common, or the second most time-consuming routine in this case was MPI com rank. And as it turns out, in this application, there were something like 35 billion calls to MPI com rank, which, if you remember, it just gives you your rank in your application back. So one individual call doesn't take much time. And most likely also the result doesn't change. But the application developers in this case just forgot to take it out, and maybe it was there for debugging purposes. And it turns out that this was actually in a production version of a code where they forgot to take it out. And at the end, it actually took up quite significant amount of time in this code. All right, so to summarize the talk, I have been trying to describe some basic concepts of performance monitoring, such as the instrumentation, measurement, and analysis parts of it. I've described the difference between profiling and tracing. I mentioned that profiling can be done both in a sampling way and a direct measurement-based approach. And I described these three tools in some detail. I should mention that there are also lots and lots of other tools. And they come basically in two different versions. One is each vendor basically has their own tool set. For example, Cray has a tool set called Cray Pat. Oracle, previously Sun, had a tool called Sun Studio. Intel has Thread Profiler, VTune, PTU, and so on. And these tools usually work pretty well. They can take advantage of the combined stack. They know what the compiler does and so on. But they are typically not very portable. So if you move from one machine to another, this particular tool might not be there or might not work so well. And so there's also a large range of independent and portable tools. In addition to the ones that I mentioned here, there's Tau, PerfSuite, Paradigm, HPC Toolkit, Kojak, Scalability, OProfile, GProf, and many others as well. And well, one current trend is GPUs are currently not so well covered in this aspect, and several people are working on extending monitoring for GPUs as well. Right, and so I thank you for your attention, and happy to take any questions.
So I was wondering, when you say that it's like lightweight and it doesn't add a lot of time, what kind of time does it add? And what, for your different programs, like the heavier profilers versus the lighter, what kind of time addition are we looking at?
So for IPM, we did some experiments and we saw that it's typically less than 0.5% of your execution time. There is a dependence on just how many times how many events happen in the program, right? IPM does something for each event, like an MPI send operation that happens. So there is a sort of a linear dependency just on how many of those you do per second or something like that. But for